What is the rarest thing in the universe? In a cosmos overflowing with countless stars, swirling galaxies, and strange celestial objects, there lies a class of stars so uncommon that their very existence seems like an astronomical miracle. These are the blue hypergiants, cosmic behemoths that burn brighter, hotter, and more powerfully than nearly anything else in the night sky. They defy normal stellar rules, existing only for a fleeting moment in the vast timeline of the universe. And yet, despite their extraordinary presence, astronomers have identified only around 30 of them across the entire observable universe. That is the cosmic equivalent of finding a handful of diamonds in an endless desert of sand. A blue hypergiant is one of the most extreme kinds of stars that the universe has ever managed to produce. When astronomers speak of these objects, they are not referring to stars that are simply larger than average, but to a class that goes beyond nearly every measurement we normally use to describe stellar bodies. A blue hypergiant is defined as an exceptionally massive and luminous star, often belonging to spectral types O or B, which indicates very high surface temperatures and a distinctive blue-white coloration. They are not just a little bigger than supergiants, they represent an entirely higher tier of stellar evolution. The term hypergiant is an official classification used by astrophysicists to describe stars with enormous luminosities and significant spectral peculiarities that suggest instability. In simpler terms, they are giants among giants, existing in a very delicate and short-lived state because of the forces tearing them apart from within. To understand what makes a blue hypergiant so different, it helps to compare them to more familiar stars. Our Sun, for example, is classified as a G-type main sequence star. It is stable, relatively small on the cosmic scale, and burns hydrogen at a steady pace. By contrast, a blue hypergiant can be tens to hundreds of times larger in radius and tens of times more massive in total mass. The energy output from such an object is almost impossible to comprehend. It is not merely thousands, but millions of times more luminous than our Sun. These stars are so powerful that their brightness can outshine entire star clusters, dominating their local cosmic neighborhood. Their enormous luminosity is one of the key reasons they are unstable, since the pressure generated by the radiation coming out of their cores constantly pushes against their gravitational pull, threatening to rip them apart. Another defining trait of blue hypergiants is their instability. While the word hypergiant already signals their size, the blue color indicates their extreme surface temperature, which is often higher than 20,000 Kelvin. This level of heat means that they are burning through their nuclear fuel at astonishing rates. Normal stars like the Sun carefully conserve their hydrogen fuel, stretching their life cycles across billions of years. A blue hypergiant, however, operates in the exact opposite way, blazing so intensely that it consumes its fuel reserves in only a few million years. For comparison, that is about 1/10,000th the lifespan of an ordinary star like our Sun. Their instability can also be seen in their violent stellar winds and frequent mass loss. These stars shed huge amounts of matter into space, often producing nebula around them that glow with the energy of the material being blasted outward. Structurally, blue hypergiants are complex. They have dense cores where nuclear fusion occurs at extreme levels, surrounded by outer layers that are continuously being pushed outward by radiation pressure. This balance between gravity pulling inward and radiation pushing outward is precarious. In many cases, their outer envelopes become unstable, leading to eruptions, variability in brightness, and in some extreme cases, sudden outbursts that temporarily change their appearance. Eta Carinae, one of the most well-studied blue hypergiants, is a perfect example. It underwent a giant eruption in the 19th century that temporarily made it the second brightest star in the night sky. Events like this are not anomalies for blue hypergiants. They are natural outcomes of the unstable conditions under which they exist. Astronomers define these stars not only by size and brightness, but also by the way their light interacts with their unstable outer atmospheres. Spectroscopic analysis shows broadened spectral lines, a signature of rapid mass loss and chaotic conditions in their outer layers. These broadened lines are what set hypergiants apart from less extreme stars, providing a measurable way for scientists to categorize them. In fact, the instability of their atmospheres is so characteristic that it is one of the defining requirements for the hypergiant classification. Without such instability, a star may be labeled as a supergiant but not elevated to the hypergiant category. From a broader perspective, defining a blue hypergiant is not just about saying it is big and bright. It is about understanding how it fits into the spectrum of stellar evolution. These stars sit at the top end of the Hertzsprung-Russell diagram, the chart astronomers use to classify stars by luminosity, temperature, and spectral type. On that chart, hypergiants occupy a space that only a handful of stars can ever reach, because very few stars are born with the mass required to become one. Even fewer survive long enough to be identified, since their instability often leads to a rapid and dramatic end. What makes them especially fascinating is that they are almost paradoxical by nature. They are incredibly powerful, yet extremely fragile. They shine with more brilliance than nearly any other kind of star, yet that very brilliance is the reason they cannot last. Their definition is, therefore, tied to their fleeting existence, a star burning so intensely that it cannot sustain itself for long. To define them is to acknowledge that they are both a product of extreme conditions and a temporary spectacle in the grand history of the universe. With the basics of what blue hypergiants are firmly established, their classification, their size, their instability, and their place in stellar evolution, we can now turn to an equally important question. Why are they so rare in the first place? The rarity of blue hypergiants is one of the most striking aspects of their existence, and it is this scarcity that elevates them to the status of some of the most extraordinary objects in the cosmos. Out of the unfathomable number of stars scattered across the observable universe, estimated at around 200 billion trillion, astronomers have identified only about 30 blue hypergiants. To put this into perspective, even exotic phenomena like neutron stars or black holes are far more common. The fact that we can count known blue hypergiants on just a few dozen fingers highlights how extreme the conditions must be for such stars to form, survive, and be observed before their inevitable collapse. The reason behind their rarity starts at the very beginning: stellar birth. To form a blue hypergiant, an enormous molecular cloud of gas and dust is required, one with far more mass than is needed to create normal stars. While small stars like red dwarfs can form under relatively modest conditions, a hypergiant demands something extraordinary, hundreds of times more raw material condensed in just the right way. Even in massive star-forming regions, it is difficult for gravity to pull together such colossal amounts of matter into a single core without the material fragmenting into many smaller stars. In most cases, the universe prefers quantity over quality, producing numerous smaller stars rather than a single gargantuan one. This is why the birth of a blue hypergiant is already an unlikely outcome. Even when such a star does manage to form, its survival is far from guaranteed. Blue hypergiants are unstable by design. The immense radiation pressure within them constantly pushes against their own gravity, making them prone to losing mass through powerful stellar winds. In fact, these stars can lose solar masses of material over the course of just a few thousand years. Many stars that start their lives on the path toward becoming hypergiants shed so much mass that they downgrade into other types of massive stars before ever reaching or sustaining hypergiant status. In other words, the conditions required for a star not only to form as a hypergiant, but also to remain one long enough for us to detect it, are exceedingly rare. Another critical factor in their scarcity is their lifespan. Normal stars like our Sun live for billions of years, giving astronomers plenty of time to spot them. Blue hypergiants, by contrast, live only a few million years at most. On cosmic timescales, this is like a blink of an eye. Because of this, the odds of humanity existing at just the right time in the universe's history to witness even a few of them is already astronomically slim. Many hypergiants have likely formed and died in the distant past, their spectacular deaths lost to time, leaving only traces in the form of nebula or black holes. The 30 or so that we know of are only the survivors that exist right now in our observational window. Detection also plays a role in their perceived rarity. Blue hypergiants are usually found in distant star clusters and galaxies, often many thousands of light years away. Their extreme luminosity makes them visible across great distances, but separating them from other bright, massive stars is not always straightforward. Detailed spectral analysis is required to confirm whether a star is indeed a hypergiant, and this kind of analysis is time-consuming and technically challenging. It's possible that there are slightly more than 30, but so far, only about that many have been confirmed. Even if the number rises slightly with future discoveries, the fact remains, they are still among the rarest types of stars in existence. What makes this scarcity so fascinating is the contrast with the abundance of stars overall. Red dwarfs, the most common type of star, make up roughly 70 to 80% of all stars in the Milky Way alone. They are everywhere, long-lived, and relatively stable. Blue hypergiants, on the other hand, represent the absolute opposite: short-lived, unstable, and vanishingly few. If the universe were a city, red dwarfs would be the countless streetlights lining every road, while blue hypergiants would be monumental skyscrapers, so rare and towering that they define the skyline, but are only ever found in small numbers. The fact that there are only about 30 blue hypergiants known in the universe is not just a statistic, it's an illustration of how extreme and selective cosmic processes can be. Out of nearly infinite possible outcomes, nature occasionally creates something that pushes against the boundaries of what stars can be, but only sparingly. Their rarity makes them vital subjects of study because every one we observe could be the key to understanding not just stellar evolution, but also the limits of matter and energy under the harshest possible conditions. With their scarcity firmly established, it is natural to wonder, what exactly do these few survivors look like in terms of scale? To answer that, we must turn to their sheer physical dimensions, where their extreme size makes them some of the most awe-inspiring objects in all of astronomy. When discussing the extreme size of blue hypergiants, it is essential to remember that we are not just talking about stars slightly larger than our Sun. We are talking about objects that completely dwarf it, both in radius and mass. A blue hypergiant can be tens to hundreds of times larger in radius than the Sun, and its mass can range from 20 to more than 100 times the Sun's mass. These numbers may sound abstract, but the scale they represent is staggering. If a blue hypergiant were placed at the center of our solar system, where the Sun is now, its surface could extend beyond the orbit of Mercury, Venus, and potentially even Earth, depending on the star's size. Our planet would either be engulfed or orbit uncomfortably close to a stellar furnace, thousands of times more destructive than anything we know. In terms of volume, the difference becomes even more incomprehensible, since the volume of a sphere increases with the cube of the radius. A star with a radius 100 times that of the Sun could contain over 1 million suns inside it. This does not mean it is solidly filled with mass, of course. Stars are gaseous bodies, with densities varying from the core to the surface. But the sheer space such a star occupies in the cosmos is enormous, dominating any stellar neighborhood it resides in. The Sun, often described as a large star in everyday conversation, becomes almost insignificant when compared to the cosmic scale of a hypergiant. The mass of a blue hypergiant adds another layer to its extreme size. While their radii can vary, their sheer weight in terms of solar masses is always colossal. A blue hypergiant with 50 or 100 times the Sun's mass is not just heavier, it is fundamentally different in its internal processes. The gravitational force at its core is so intense that nuclear fusion occurs at vastly accelerated rates. This immense mass also means their gravitational influence extends far beyond what our Sun commands. In a cluster, a hypergiant can dominate the orbits and behavior of neighboring stars, acting as a gravitational anchor despite its relatively short lifespan. One fascinating aspect of their size is that it directly contributes to their instability. Stars that large are constantly battling a delicate balance between gravity pulling inward and radiation pressure pushing outward. In smaller stars, like the Sun, gravity wins comfortably most of the time, keeping the star in stable equilibrium. In a blue hypergiant, however, the energy being produced in the core is so immense that the outer layers are perpetually under stress, often resulting in mass ejections and unstable fluctuations. In essence, their very size makes them unsustainable, a natural contradiction written into their being. Astronomers often compare blue hypergiants to other large stars to highlight their scale. For example, red supergiants like Betelgeuse can also be enormous in terms of radius, sometimes even larger than hypergiants. However, blue hypergiants combine both extreme mass and extreme luminosity, which sets them apart. A red supergiant may be swollen and vast, but it does not have the same ferocious energy output. Blue hypergiants are not just bloated stars. They are compact enough to maintain blistering heat and dense enough to sustain powerful nuclear burning at their cores. This makes them some of the most extreme objects in the Hertzsprung-Russell diagram, occupying a zone reserved for only the most massive and luminous stellar entities. What's even more remarkable is that despite their massive size, they are still young in stellar terms. Blue hypergiants often form in large clusters of stars, and their size gives them immediate dominance in those environments. They can shape the evolution of their cluster through their intense radiation, stellar winds, and eventual supernova explosions. Their size is not just an individual trait, it becomes a force that influences everything around them. The gas clouds from which other stars may form can be eroded or compressed by the hypergiant's energy, meaning these colossal stars literally shape the next generation of stellar birth in their regions. The sheer physical dominance of blue hypergiants demonstrates why they are considered extreme outliers in the catalogue of known stars. Their enormous size makes them unstable, their mass fuels violent processes, and their gravitational and radiative presence ensures that they change everything around them. Their size alone would make them noteworthy, but in combination with their other traits, it positions them as some of the most extraordinary phenomena in the universe. Having established the mind-boggling scale of blue hypergiants, the next step is to understand not just how large they are, but how blindingly luminous they become because of their massive size and furious nuclear burning. The luminosity of blue hypergiants is one of their most defining and awe-inspiring characteristics. While their size and mass already place them in a league of their own, it is their staggering brightness that truly sets them apart from almost every other type of star in the universe. To put it simply, a blue hypergiant shines with a luminosity that can be millions of times greater than that of our Sun. This means that a single hypergiant has the energy output equivalent to what millions of suns produce combined. From an astronomical perspective, they are veritable beacons of energy, pouring radiation into their surrounding space at levels that almost defy comprehension. This overwhelming luminosity is a direct consequence of both their size and their surface temperature. Blue hypergiants typically have surface temperatures exceeding 20,000 Kelvin, much hotter than the Sun's relatively mild 5,778 Kelvin. According to the Stefan-Boltzmann law, the energy output of a star increases rapidly with both surface area and temperature. Since hypergiants are not only vastly larger in radius, but also significantly hotter, their luminosity skyrockets to unimaginable levels. This combination of size and temperature creates a feedback loop. More surface area emits more energy, and higher temperature ensures that energy is emitted at shorter, more energetic wavelengths, making the star blaze with extraordinary intensity in the ultraviolet and visible spectrum. From a practical standpoint, the luminosity of a blue hypergiant means that it can be detected across tens of thousands of light years. Unlike dim stars, which fade into obscurity outside of nearby space, blue hypergiants project their brilliance so powerfully that astronomers can spot them in distant galaxies. This visibility has been crucial to their discovery because while they are exceedingly rare, their brightness ensures they stand out even in crowded star fields. In some star clusters, a hypergiant can outshine all its neighbors combined, becoming the focal point of the entire region. Eta Carinae, one of the most famous examples, at its peak brightness in the 19th century became the second brightest star in the night sky, even though it is located about 7,500 light-years away. That is the kind of blinding luminosity we are dealing with. Light so powerful, it can dominate human vision from unfathomable distances. The brightness of a blue hypergiant is not steady, however. Their luminosity is often subject to variability because the same instability that defines them also affects their light output. Periodic eruptions, stellar winds, and mass ejections can cause changes in brightness on timescales ranging from months to centuries. These fluctuations do not diminish their overall luminosity. Instead, they make them even more fascinating to astronomers, since such changes are windows into the chaotic processes occurring within and around the star. For example, Eta Carinae's great eruption in the 1800s temporarily made it almost rival Sirius, despite being vastly farther away. Such behavior is a vivid demonstration of how their luminosity is not just immense, but also dynamic. Their blinding brilliance has consequences for their surroundings as well. The radiation emitted by a blue hypergiant exerts enormous pressure on nearby matter. Surrounding dust clouds can be heated, ionized, and pushed away, effectively carving out cavities in the interstellar medium. The ultraviolet radiation they emit is capable of stripping electrons from atoms, creating ionized regions of gas that glow brightly, often visible as nebulae. This means that their luminosity is not just a spectacle to distant observers like us. It is a force that reshapes their local cosmic environment. Star formation in the same region can be disrupted or enhanced, depending on how the hypergiant's light interacts with nearby material. One might assume that such staggering brightness should make them common in the night sky, yet the opposite is true. Their rarity means that even though each one blazes with the light of millions of suns, we only see a handful from Earth. To put this in perspective, the Milky Way alone contains between 100 and 400 billion stars, yet only a few confirmed blue hypergiants reside within it. Their luminosity makes them visible from extraordinary distances, but their scarcity ensures that spotting one is still a rare privilege. Astronomers study this luminosity carefully because it offers insights into the physics of stellar energy production. A star that shines millions of times brighter than the Sun is clearly operating under extreme conditions. Understanding how such energy is generated and sustained, even for a short cosmic time, provides clues about nuclear fusion rates, stellar structure, and the ultimate limits of what stars can achieve before tearing themselves apart. These studies also help refine the models used to predict the evolution of massive stars, since luminosity is directly tied to how quickly a star consumes its nuclear fuel. In essence, the blinding luminosity of blue hypergiants is both their glory and their downfall. It makes them some of the most extraordinary sights in the universe, capable of outshining entire clusters and visible across intergalactic distances. But it also ensures that they live precarious, short lives, as no star can burn so furiously for long without exhausting itself. And that brings us to one of the most defining traits of these cosmic titans, the short lifespan that marks their inevitable and dramatic end. The short lifespan of blue hypergiants is one of the most striking differences between them and ordinary stars like our Sun. While our Sun is expected to live for around 10 billion years, blue hypergiants burn out in just a few million years at most. To put that into perspective, if the Sun's life were a long human lifespan of 80 years, a blue hypergiant would live less than a single year. Their lives are not measured in billions or even hundreds of millions of years. They are measured in fleeting bursts of cosmic time, and that brevity is tied directly to the extreme way in which they consume their nuclear fuel. Stars shine because of nuclear fusion, the process of fusing hydrogen into helium in their cores, which releases enormous amounts of energy. Smaller stars, such as red dwarfs, burn their hydrogen slowly and carefully, stretching their lifespans to trillions of years. Medium-sized stars like the Sun also manage their fuel efficiently, lasting billions of years. Blue hypergiants, however, are on the opposite end of the spectrum. With masses 20 to more than 100 times greater than the Sun, their cores are subjected to such intense gravitational pressure that nuclear fusion runs at a furious pace. The more massive the star, the faster it burns its fuel, and in the case of blue hypergiants, this process is so accelerated that they consume vast amounts of hydrogen in just a few million years. Their enormous luminosity is both a symptom and a cause of their short lives. To shine millions of times brighter than the Sun requires releasing energy at unimaginable rates, and that energy comes directly from nuclear fusion in their cores. The brighter the star, the faster it eats through its hydrogen. Once the hydrogen supply in the core runs out, the star has no choice but to move on to heavier elements such as helium, carbon, and oxygen. These stages of fusion are progressively shorter because each successive element yields less energy than hydrogen. As a result, the life of a blue hypergiant is not just short overall, but it becomes even shorter as it approaches its final stages. Another factor contributing to their short lifespans is their instability. Blue hypergiants are not calm, steady stars. They constantly lose material through powerful stellar winds and eruptions. In some cases, they shed several solar masses of gas in just a few thousand years. This rapid mass loss not only reduces their fuel supply, but also destabilizes their outer layers, causing fluctuations in brightness and structure. In extreme cases, eruptions can eject enough mass to alter the star's evolution entirely, forcing it into new phases earlier than it otherwise would have entered them. Their instability is essentially a constant drain on their existence, accelerating their already short timelines. Their lifespans are also cut short because the most massive stars exist close to the Eddington limit, the point at which the outward pressure of radiation nearly equals the inward pull of gravity. Operating so close to this limit means that even small fluctuations can result in mass loss or instability, reducing their ability to maintain equilibrium for long. Where smaller stars comfortably balance their energy output and gravitational structure, hypergiants are constantly on the edge of collapse or eruption. This precarious balance speeds up their path toward death, making their life cycles some of the shortest in the universe for any star of significant mass. What makes their brief lives even more dramatic is that they often end in spectacular ways. Unlike the Sun, which will quietly shed its outer layers and become a white dwarf, blue hypergiants almost always conclude their existence with violent supernova explosions, or even direct collapse into black holes. In some cases, they may explode as hypernovae, some of the most energetic explosions ever observed, releasing more energy in a few seconds than the Sun will release in its entire 10 billion year lifetime. Their short lifespans are not quiet disappearances. They are fiery conclusions that reshape their surrounding environments and seed the cosmos with heavy elements. When comparing lifespans across different types of stars, the extremes become clear. Red dwarfs, which make up the majority of stars in the universe, live for trillions of years. Sun-like stars live for billions. Even massive red supergiants can last tens of millions of years before exploding. Blue hypergiants, by contrast, are the shortest-lived of them all. Their short existence is not a weakness, but a consequence of their sheer power. They are the ultimate example of living fast and dying young, burning with extraordinary brilliance but unable to sustain themselves for long. This brevity is part of what makes them so rare and precious to astronomers. The universe has existed for 13.8 billion years, and we happen to exist during a tiny sliver of time in which a handful of these giants are still alive and visible. That coincidence is remarkable, because the vast majority of blue hypergiants that have ever existed have already burned out and died, leaving behind black holes, neutron stars, or remnants of supernova explosions. Their short lifespans highlight the fragile balance that defines these cosmic titans. They are massive enough to achieve unmatched brightness and size, but that very mass ensures their quick demise. With this understanding of their fleeting existence, the next step is to look deeper into the stellar instability that drives their unpredictability and shapes their violent evolution. The instability of blue hypergiants is one of the most defining aspects of their nature, and it is inseparably tied to the way they burn their fuel at such extraordinary rates. These stars are, by their very makeup, volatile objects, never truly in balance, always teetering on the edge of chaos. While most stars achieve a long-lasting equilibrium between the inward pull of gravity and the outward push of radiation, blue hypergiants exist in a precarious state where their massive energy output constantly disrupts this balance. Their instability is not a minor characteristic. It is central to why they are rare, short-lived, and ultimately so spectacular. At the heart of a blue hypergiant, the fusion process is occurring at an accelerated pace, unlike almost any other kind of star. The enormous gravitational pressure created by their immense mass forces atoms together in the core at blistering rates. Hydrogen, the primary fuel, is fused into helium in an incredibly short time compared to normal stars. This process releases unimaginable amounts of energy, but it comes at a cost. The faster the fuel burns, the less time the star can remain stable. In a way, blue hypergiants are stars that are overproducing energy, consuming themselves from within. Where the Sun has a steady budget of fuel lasting billions of years, a hypergiant spends everything it has in just a few million. This excessive fuel consumption leads to turbulence throughout the star. The radiation pressure produced inside constantly pushes outward against the pull of gravity, and this battle is never quite settled. Sometimes radiation wins, driving powerful outflows of gas into space, while at other times gravity briefly reasserts control. The result is a star that experiences frequent fluctuations and eruptions. Unlike stable stars with predictable brightness, hypergiants often undergo changes in luminosity as their outer layers expand, contract, and occasionally explode outward. This is why some blue hypergiants are classified as variable stars, objects whose brightness changes over time due to internal instability. One visible consequence of this instability is their stellar winds. Blue hypergiants produce some of the strongest stellar winds in the universe, ejecting matter into space at speeds of thousands of kilometers per second. Over time, these winds strip away significant portions of the star's mass, creating surrounding shells or nebulae of gas and dust. These winds are not a gentle breeze, but a storm so fierce that it can carry away the equivalent of the Sun's mass over just a few 100,000 years. The instability fueling these winds ensures that the star is continuously shedding layers of itself, almost as if it cannot contain its own power. Another hallmark of instability is the occurrence of eruptive events. Eta Carinae, one of the most famous blue hypergiants, underwent a massive eruption in the 1840s, known as the Great Eruption, during which it expelled several solar masses of material in just a few decades. For a time, it became one of the brightest objects in the sky, rivaling Sirius, despite being thousands of light years away. This eruption created the Homunculus Nebula, a pair of massive gas lobes that still surround Eta Carinae today. Such outbursts are a direct manifestation of stellar instability, revealing that blue hypergiants can undergo sudden, dramatic changes as their inner equilibrium collapses and reforms. The instability extends to their internal structure as well. Unlike smaller, stable stars where layers are clearly defined, blue hypergiants often experience mixing of material between the core and outer layers. This mixing alters their chemical composition, affecting the way they evolve. It also destabilizes their fusion process, since material from outer layers can move inward and accelerate burning cycles. This chaotic circulation contributes to their unpredictability, making their long-term behavior far more difficult for astronomers to model compared to less massive stars. On a larger scale, the instability of blue hypergiants is tied to their proximity to the Eddington limit, the point where outward radiation pressure is nearly equal to inward gravitational pull. Because they are so close to this threshold, even slight changes in fusion rates or mass distribution can tip the balance, triggering episodes of mass loss, variability, or catastrophic eruptions. Essentially, these stars live on the edge of collapse for their entire lives. They are powerful enough to shine with the light of millions of suns, but that power constantly undermines their stability. This relentless instability makes blue hypergiants crucial subjects for astrophysics. By studying their unpredictable nature, astronomers gain insights into how massive stars live and die, how they shed mass, and how they contribute to the chemical enrichment of galaxies. Their instability is not just a destructive trait, it also ensures that they are major contributors to the cosmic cycle, preparing the way for the next generations of stars. With their unstable nature now clear, the next defining characteristic to examine is their surface temperatures, which rise to some of the highest levels of any star in the universe, adding yet another extreme to their profile. The surface temperatures of blue hypergiants are another measure of their extreme nature, and they are nothing short of staggering. While our Sun maintains a relatively modest temperature of about 5,778 Kelvin at its surface, blue hypergiants often exceed 20,000 Kelvin, with some even reaching 40,000 Kelvin or more. To grasp the scale of this difference, it helps to understand that the Kelvin scale is an absolute measure of temperature, starting from absolute 00, where all molecular motion ceases. At these blistering levels, the outer layers of a blue hypergiant are not merely hot, they are superheated plasma radiating at levels that can strip electrons from atoms and generate intense ultraviolet and even far ultraviolet light. This extreme temperature is the result of their enormous mass and furious fusion rates. In smaller stars like the Sun, The rate of hydrogen fusion is steady and controlled, producing moderate surface temperatures. In blue hypergiants, however, the immense gravitational pressure at the core forces fusion to occur at a much higher rate, releasing extraordinary amounts of energy. That energy flows outward, heating the star's outer layers to temperatures many times higher than what we are accustomed to in ordinary stars. The higher the mass of the star, the greater the pressure and the greater the heat produced. The result is a searing surface that makes blue hypergiants some of the hottest stars in the universe. Their scorching heat is directly tied to their color and spectral classification. Stars emit different colors of light depending on their temperature, with cooler stars appearing red or orange, medium stars like the Sun appearing white, and hotter stars appearing blue or violet yellow-white, and hotter stars appearing blue or blue-white. Blue hypergiants fall into the O and B spectral classes, meaning they are among the hottest of all stars. The blue in their name is not symbolic, but a literal indicator of their surface temperature. The human eye perceives their overwhelming emission in the blue and ultraviolet part of the spectrum, giving them their distinctive bluish-white glow when viewed through telescopes. One fascinating aspect of these surface temperatures is their effect on the star's radiation output. The hotter a star's surface, the shorter the wavelengths of light it emits. While the Sun emits most of its energy in the visible spectrum, blue hypergiants emit much of their radiation in the ultraviolet range. This makes them far more energetic than their brightness in visible light alone would suggest. Their UV radiation is powerful enough to ionize gas in their surroundings, creating glowing nebulae and altering the chemical and physical properties of nearby interstellar material. Essentially, their heat allows them to act as engines of ionization, reshaping their local environments in ways smaller, cooler stars never could. These scorching surface conditions also contribute to the stellar winds that define blue hypergiants. At temperatures above 20,000 Kelvin, the outer layers of the star are so energized that atoms are constantly being accelerated to escape velocities. This creates outflows of material traveling at thousands of kilometers per second, carrying away huge amounts of mass from the star. In some cases, these stellar winds are so intense that they form massive envelopes of gas and dust around the star, like the homunculus nebula surrounding Eta Carinae. The link between surface temperature and stellar wind is direct. The hotter the surface, the stronger the radiation pressure, and the more violent the mass loss becomes. Surface temperature also affects how blue hypergiants evolve over time. As they burn through their fuel and undergo changes in their internal structure, their temperatures can shift. Some blue hypergiants oscillate between hotter and cooler phases, temporarily resembling different classes of stars. This variability, driven by internal instability, makes them even more unpredictable. Nonetheless, their baseline surface temperatures remain among the highest of any known stars, a constant reminder of the immense energy pouring out from within. Astronomers rely on these temperatures as a diagnostic tool. By analyzing the light from a blue hypergiant using spectroscopy, scientists can determine not only its surface heat, but also its chemical composition, rate of mass loss, and even clues about its age and stage of evolution. The incredibly high surface temperatures are not just a number, they are a fingerprint that tells the story of the star's extreme internal processes. Ultimately, the scorching surface of a blue hypergiant is one more way these stars push the boundaries of what is possible in stellar physics. They are hotter, brighter, and more violent than nearly any other type of star, and their heat is a fundamental driver of their instability and destructive power. This immense surface temperature, coupled with their massive size and luminosity, makes them not only dangerous to themselves, but also to their surroundings, where their radiation and stellar winds transform entire regions of space. With their searing heat now clear, the next logical step is to explore how these temperatures feed into their role as cosmic powerhouses, where their extreme stellar winds and outflows reshape the universe around them. Blue hypergiants are not only defined by their immense size, luminosity, and heat, they are also cosmic powerhouses, unleashing some of the most extreme stellar winds in the universe. These stellar winds are not comparable to the solar wind we experience from the Sun, which consists of streams of charged particles flowing outward at moderate speeds. Instead, the winds from a blue hypergiant are violent torrents of matter, driven by the star's blistering heat and blinding luminosity, and they reach speeds of thousands of kilometers per second. The sheer force of these outflows is enough to strip away the star's outer layers, ejecting enormous amounts of mass into space and reshaping its immediate cosmic environment. At the heart of these winds is the radiation pressure produced by the star's extraordinary luminosity. With surface temperatures exceeding 20,000 Kelvin and energy output millions of times that of the Sun, blue hypergiants bombard their outer layers with such intense radiation that atoms are pushed outward at escape velocities. Photons, particles of light, transfer momentum to the stellar material, accelerating it away from the star. This process is amplified in hypergiants because their luminosity is so close to the Eddington limit, the threshold at which radiation pressure nearly cancels out the force of gravity. As a result, even a slight surplus of radiation can hurl matter into space, creating winds that dwarf those of almost any other star type. The scale of these winds is difficult to comprehend. While the Sun loses about 1/10,000,000th of its mass per year through solar wind, a blue hypergiant can lose the equivalent of the Sun's mass in just a few tens of thousands of years. In some particularly unstable cases, like Eta Carinae, the star can eject multiple solar masses of gas in a single eruptive event. Over its short lifetime, a hypergiant may shed a significant fraction of its total mass, drastically altering its evolution and preparing the way for its eventual explosive demise as a supernova or hypernova. These stellar winds do not simply disappear into the void. They have profound effects on the regions of space surrounding the star. The material ejected by a blue hypergiant often forms vast nebulae, glowing clouds of gas and dust illuminated by the star's radiation. The homunculus nebula, surrounding Eta Carinae, is a striking example. A pair of massive lobes of gas and dust created during the star's great eruption in the 19th century. Such structures are both beautiful and scientifically valuable, serving as records of the star's unstable history and as laboratories for studying the dynamics of high-energy stellar winds. These winds also play a crucial role in the chemical enrichment of the universe. Blue hypergiants are capable of fusing elements heavier than hydrogen and helium in their cores, and their stellar winds spread some of these elements into the interstellar medium, even before the star reaches its final collapse. By ejecting carbon, nitrogen, oxygen, and other heavier elements, they contribute directly to the cosmic cycle that allows new stars, planets, and eventually life itself to form. Their winds are not only destructive, they are also creative, seeding the universe with the building blocks of future generations of stars and systems. Another effect of these powerful winds is their ability to shape star-forming regions. In large star clusters, where hypergiants often reside, their winds can compress nearby gas clouds, triggering the formation of new stars, or they can disperse these clouds entirely, halting star formation in that area. In this sense, blue hypergiants act as architects of their galactic neighborhoods, using their energy and mass loss to control the pace of star birth around them. Few stars wield such influence, and this is why they are considered not just individual phenomena, but cosmic engines. Astronomers study these winds using spectroscopy, which reveals the speed, density, and composition of the outflowing material. Observations often show broadened absorption lines in the star's spectrum, a signature of material being ejected at incredible velocities. These measurements allow scientists to quantify how much mass is being lost and how fast, giving crucial insights into the life cycle of hypergiants. Understanding these winds also helps refine models of how stars transition from one evolutionary phase to another, since mass loss is often the deciding factor in whether a star becomes a supernova, collapses into a black hole, or follows some other path. The stellar winds of blue hypergiants are thus one of their most important defining features. They are not gentle breezes, but catastrophic storms, stripping the stars of their mass, sculpting nebulae, and influencing entire regions of galaxies. This relentless outflow of matter makes them true powerhouses of the cosmos, ensuring that their influence extends far beyond their short lives. Having seen how their winds propel matter and energy into the universe, it becomes natural to step back and compare their incredible power with something more familiar: our own Sun. When comparing blue hypergiants to our Sun, the differences are so vast that it almost feels like we are discussing two entirely different categories of objects rather than two examples of the same stellar phenomenon. The Sun, which we often consider massive and powerful because it sustains all life on Earth, is in reality a medium-sized star, stable and relatively quiet when placed against the backdrop of cosmic giants. Blue hypergiants, on the other hand, represent the extreme end of what stars can become: immense, unstable, and burning with a fury millions of times greater than the Sun could ever achieve. In terms of size and mass, the Sun is almost insignificant compared to a blue hypergiant. The Sun has a radius of about 696,000 kilometers, but a blue hypergiant can have a radius tens or even hundreds of times larger. If one of these hypergiants were to replace the Sun at the center of our solar system, its surface might extend well beyond the orbit of Mercury, Venus, and in some cases, even Earth. Mass is another measure where the difference is staggering. The Sun's mass is about one solar mass by definition, while a blue hypergiant can be anywhere from 20 to more than 100 solar masses. This immense mass fuels the hypergiant's explosive energy output, but also destabilizes it, unlike the Sun's more modest and sustainable design. The contrast becomes even more dramatic when we consider luminosity. Our Sun shines with a steady brilliance that is sufficient to illuminate Earth and the rest of the solar system. However, a blue hypergiant shines with a luminosity millions of times greater than the Sun's. This means that in 1 second, a hypergiant emits as much energy as the Sun produces in millions of seconds. The Sun, for all its importance to us, is practically a candle flame compared to the raging inferno of a hypergiant. This brightness allows hypergiants to be seen across vast distances of the galaxy and even in neighboring galaxies, while the Sun is visible only to those within its immediate solar system. Surface temperature also separates the two. The Sun's surface temperature is about 5,778 Kelvin, giving it a yellowish-white glow. Blue hypergiants, with temperatures exceeding 20,000 Kelvin, glow with a blue-white light that indicates much higher energy radiation. This difference not only affects their appearance, but also the type of energy they emit. While the Sun radiates primarily in the visible spectrum, hypergiants pour out enormous amounts of ultraviolet radiation, strong enough to ionize nearby gas clouds and dramatically shape their environments. In terms of lifespan, the difference is perhaps the most profound. The Sun is expected to live for about 10 billion years, with nearly 5 billion years of stable life still ahead. Blue hypergiants, by contrast, live for only a few million years, a tiny fraction of the Sun's timeline. This is because the Sun burns its fuel slowly and steadily, conserving energy over eons, while hypergiants consume their fuel in violent, accelerated bursts. Where the Sun can be compared to a marathon runner pacing itself for endurance, a blue hypergiant is like a sprinter giving everything in a short, fiery dash. Stability is another major distinction. The Sun is remarkably stable, with only minor fluctuations in solar activity that produce sunspots, solar flares, and the solar wind. These variations can affect Earth's space weather, but do not threaten the Sun's equilibrium. Blue hypergiants, however, are inherently unstable, experiencing frequent eruptions, mass loss, and fluctuations in brightness. Some, like Eta Carinae, undergo dramatic outbursts that temporarily transform their appearance, something our Sun has never experienced and never will. Even the stellar winds are drastically different. The Sun emits a solar wind that, while influential in shaping planetary magnetospheres and creating auroras, is weak compared to the torrents expelled by hypergiants. A blue hypergiant's winds are so violent that they can eject entire solar masses of material in just a few thousand years. Where the Sun's wind sculpts the edges of the heliosphere, a hypergiant's winds carve vast nebulae and reshape their local galactic environments. The death of each star underscores the contrast. The Sun will eventually expand into a red giant, shed its outer layers gently, and settle down as a white dwarf surrounded by a planetary nebula, a relatively quiet and graceful end. A blue hypergiant, however, almost always dies explosively, collapsing into a black hole or neutron star after unleashing a supernova or even a hypernova. The Sun will leave behind a small, dim remnant. The hypergiant will end its life in a titanic explosion that can outshine entire galaxies for weeks. In every possible metric, size, mass, luminosity, temperature, stability, lifespan, and death, the Sun and blue hypergiants occupy opposite ends of the stellar spectrum. The Sun is steady, reliable, and enduring. Blue hypergiants are extreme, unstable, and fleeting. Both are important in their own ways. The Sun sustains life and provides a stable example of stellar physics, while blue hypergiants showcase the outermost limits of what stars can achieve before collapsing under their own power. Having contrasted their immense scale and power with the Sun, the next step is to examine where blue hypergiants are found in the cosmos, since their rarity and brilliance often place them in some of the universe's most dynamic regions. Blue hypergiants are not the kind of stars you will find in our solar neighborhood, nor even within the average quiet regions of the Milky Way. Their rarity, immense mass, and short lifespans mean they appear only under very specific cosmic conditions, and as a result, they are primarily located in distant star clusters and galaxies, far from the calm environment we inhabit. While ordinary stars like red dwarfs and Sun-like stars are scattered almost everywhere, blue hypergiants are concentrated in places where the raw ingredients and extreme conditions needed for their formation exist. Their scarcity and distribution reflect just how selective the universe is when creating these colossal cosmic titans. To understand where blue hypergiants are found, it helps to consider how they form. Stars come into existence when dense clouds of gas and dust collapse under the force of gravity, igniting nuclear fusion in their cores. For most stars, this process is relatively straightforward, and the universe favors the production of smaller, long-lived stars like red dwarfs. But to form a blue hypergiant requires something far more unusual, a molecular cloud with immense mass and the right balance of density and conditions to produce a star that begins its life already tens of times more massive than the Sun. Such massive star-forming regions are not common, which is why blue hypergiants are rare in the first place. They appear only in the largest and most active stellar nurseries, often inside or near young star clusters where multiple massive stars are born together. Within our own Milky Way galaxy, astronomers have confirmed only a small handful of blue hypergiants, and they are all located at great distances from Earth. For example, Eta Carinae, one of the most famous blue hypergiants, is situated about 7,500 light-years away in the Carina Nebula, an active star-forming region. The Carina Nebula itself is a stellar nursery filled with massive stars, gas clouds, and energetic radiation, the perfect breeding ground for a hypergiant. Other examples, such as HD 80077 and BP Crucis, are also found in star-forming regions or associations of massive stars. These stars are so distant that they can only be studied using large telescopes and detailed spectroscopic techniques. No blue hypergiants exist anywhere near our solar system, and certainly none within a few hundred light-years, because the conditions for their birth simply do not exist in our neighborhood. Outside the Milky Way, astronomers have also identified blue hypergiants in neighboring galaxies, such as the Large Magellanic Cloud, LMC, and the Small Magellanic Cloud, SMC, two dwarf galaxies orbiting the Milky Way. These galaxies are rich in massive star-forming regions, and their relative proximity to us, about 160,000 and 200,000 light-years away respectively, makes them prime hunting grounds for astronomers searching for hypergiants. In fact, several well-known hypergiants, such as HD 33,579 in the LMC, are located there. These stars serve as important laboratories for studying massive stellar evolution because they can be observed in environments with slightly different chemical compositions compared to the Milky Way. Looking even farther afield, hypergiants have been detected in distant galaxies millions of light-years away. Because they shine millions of times brighter than the Sun, their light can travel vast distances and still be picked up by our instruments. However, confirming them as hypergiants requires precise spectroscopic data, which is harder to obtain at such distances. Even so, their incredible luminosity allows astronomers to spot them in other galaxies, and each confirmed detection expands our understanding of how rare and special they truly are. In every case, they are found in dense star-forming regions rather than quiet galactic suburbs like the one the Sun inhabits. The environments where blue hypergiants are located also play a role in their instability and evolution. In star clusters filled with other massive stars, the radiation, stellar winds, and supernova explosions of nearby neighbors can affect a hypergiant's development. These regions are often chaotic, with vast clouds of gas and dust being constantly shaped and reshaped by powerful forces. Hypergiants in such places are not solitary. They are part of a larger ecosystem of massive stars, each influencing the other. Their locations highlight that these stars are not isolated accidents, but products of environments capable of producing the most extreme stellar objects in the universe. Another important point about their location is their distance from Earth. While we can study nearby stars like the Sun in detail with relative ease, studying blue hypergiants requires powerful observatories. Telescopes like the Hubble Space Telescope and the James Webb Space Telescope have been invaluable in observing these distant giants. Ground-based observatories, equipped with advanced spectrographs, also play a key role. Despite their immense brightness, their great distances mean they appear faint to the naked eye, and only with careful observation can we truly unravel their secrets. Their remoteness adds to their mystique. These are stars that we can never hope to approach, but only study from afar. It is also telling that no blue hypergiants are found in the immediate vicinity of Earth, because our part of the galaxy is not a region of intense star formation. The Sun resides in a relatively calm area of the Milky Way's disk, far from the giant molecular clouds that give birth to massive stars. This calmness is partly why life on Earth has had the chance to develop undisturbed by nearby supernovae or hypergiant outbursts. In contrast, the regions where hypergiants are found are often hostile environments with high levels of radiation and violent stellar activity. Their very presence indicates that these regions are hubs of stellar creation and destruction, the opposite of the relative stability we enjoy in our solar neighborhood. With their locations established, we return once again to their rarity. Knowing where they form and why they are so few leads us naturally into the next point: the role of rarity in making blue hypergiants some of the most extraordinary stars we have ever observed. The role of rarity in defining blue hypergiants cannot be overstated. Their scarcity is not just a numerical curiosity, it is the very essence of what makes them so extraordinary. In a universe with an estimated 200 billion trillion stars, the fact that only about 30 blue hypergiants are confirmed to exist is astonishing. Their rarity is the combined result of strict formation requirements, extreme physical characteristics, and their fleeting lifespans. Each of these factors alone would limit their numbers. Together, they make them among the rarest stellar phenomena in the observable cosmos. The first reason for their rarity lies in how they form. Creating a blue hypergiant requires an enormous reservoir of raw material, far larger than what is needed to form normal stars. In most cases, when molecular clouds collapse under gravity, the material fragments into many smaller stars. The universe naturally favors this outcome because it is far more stable and efficient. Producing a hypergiant, however, demands that an unusually massive portion of the cloud collapse into a single star. This is a rare outcome, even in massive star-forming regions. Only in the densest, most turbulent nurseries, often located in the spiral arms of galaxies or in active starburst regions, does such an event take place. Even then, not every massive star that forms becomes a hypergiant. Only those that reach the highest mass ranges and retain enough of their outer layers, despite constant instability, earn that classification. The second reason is their instability. Blue hypergiants exist near the very limit of what stars can physically endure. Their enormous luminosity pushes against their own gravity, constantly driving off material through stellar winds and eruptions. This instability often prevents them from sustaining themselves in the hypergiant state for long. Many stars that might otherwise qualify lose so much mass that they evolve into slightly less extreme categories before we have a chance to observe them. In other words, many potential hypergiants burn too bright and fast to ever be identified as such. Their instability is a double-edged sword. It makes them spectacular to observe, but also ensures they remain rare. Their short lifespans compound this rarity. With only a few million years to live, compared to billions for stars like the Sun, the odds of catching a blue hypergiant in its brief window of existence are extremely slim. The universe is 13.8 billion years old, and countless hypergiants have already lived and died, their existence revealed only indirectly through the supernovae and black holes they left behind. The fact that humanity happens to exist during a time when even 30 of these stars are alive and observable is an incredible stroke of cosmic timing. If we were born just a few million years earlier or later, some of these hypergiants might not be there to study, and others might not have formed yet. Their rarity also comes from observational challenges. Blue hypergiants are often located in distant regions, buried within dense star clusters, or enshrouded by the gas and dust they themselves eject. This makes them difficult to detect and confirm. Even with their enormous brightness, distinguishing them from other massive stars requires careful spectroscopic analysis, and only the most advanced telescopes are capable of such work. There may be a few more hypergiants awaiting discovery, but the fact that so far only about 30 have been confirmed underscores how rare they are. even within the most favorable conditions. The statistical contrast with other stars drives the point home. Red dwarfs, the most common stars, make up 70 to 80% of all stars in the Milky Way alone, numbering in the hundreds of billions. Sun-like stars are also common, numbering in the billions. Even exotic objects like neutron stars and stellar mass black holes are far more numerous than blue hypergiants. These other stellar populations remind us just how unusual it is for the universe to produce a star that is both so massive and so luminous. Blue hypergiants occupy the extreme tip of the stellar spectrum, and their rarity reflects that unique position. Their scarcity has scientific significance as well. Because so few exist, each one becomes an invaluable case study for astronomers. Every confirmed hypergiant is like a rare fossil to a paleontologist or a priceless artifact to an archaeologist. It provides crucial data that cannot be obtained elsewhere. Eta Carinae, for example, has been studied intensively for decades, and yet it continues to surprise astronomers with its eruptions, variability, and instability. Each rare hypergiant offers a window into the upper limits of stellar physics, teaching us about the processes that govern massive stars, the mechanisms behind supernovae, and even the creation of heavy elements that enrich galaxies. The rarity of blue hypergiants also adds to their awe factor. Knowing that we can look up at the night sky and, with the aid of telescopes, observe something so exceptional makes them stand out even more. They are not common backdrops to the galaxy, but rare jewels scattered sparingly across the cosmos. Their very scarcity heightens their value, not just scientifically, but in the broader story of how we humans connect with the universe. In the grand narrative of cosmic phenomena, blue hypergiants remind us that rarity often coincides with extremity. They represent the universe pushing the limits of what stars can be, but in doing so, they create conditions so unsustainable that only a few can ever exist at once. We are, in every sense, fortunate to live in a time where about 30 of these titans are alive, visible, and close enough to be studied. Their rarity ensures that each one carries outsized importance, not just as a spectacle, but as a key to unlocking some of the deepest mysteries of stellar evolution. Now that we understand why they are so rare and why we are lucky to observe even a handful, the next stage of their story takes us to their final act. Their spectacular deaths, some of the most powerful explosions the universe has ever witnessed. The spectacular deaths of blue hypergiants are as extreme and violent as their short, turbulent lives. Unlike stars like our Sun, which end their lives quietly, fading into white dwarfs after gently shedding their outer layers, blue hypergiants go out in titanic explosions that shake the very fabric of their galactic neighborhoods. Their immense mass ensures that when their fuel finally runs out, the end is not peaceful, it is catastrophic. These stars often die in supernovae, hypernovae, or direct collapses into black holes, leaving behind not only cosmic wreckage, but also some of the most powerful events in the known universe. The process begins with their core evolution. Blue hypergiants burn through their hydrogen fuel in just a few million years, forcing them to quickly move on to fusing heavier elements such as helium, carbon, oxygen, and silicon. Each successive stage of fusion happens faster than the last because less energy is produced with each heavier element. Eventually, the core builds up iron. Iron fusion does not produce energy, it consumes it. At this point, the delicate balance between outward radiation pressure and inward gravitational collapse can no longer be maintained. The core becomes unstable, and in a fraction of a second, gravity wins. When the core collapses, the outer layers of the star are suddenly unsupported, and they come crashing inward before rebounding outward in a supernova explosion. This event is unimaginably powerful, releasing more energy in a few seconds than the Sun will emit over its entire 10 billion-year lifetime. For a brief period, the explosion can outshine an entire galaxy of billions of stars. The shockwave tears apart the star's outer layers, blasting them into interstellar space at incredible speeds. The remnants of this explosion enrich the surrounding galaxy with heavy elements, gold, uranium, and other materials that cannot form in normal stellar processes, but are instead forged in the extreme conditions of a supernova. In some cases, the explosions of blue hypergiants are not ordinary supernovae, but hypernovae, which are even more energetic. A hypernova is capable of producing gamma-ray bursts, the most powerful bursts of energy known in the universe, observable across billions of light-years. These events are rare but devastating, pouring out intense radiation that can sterilize entire regions of space if planets are unlucky enough to be in their path. Astronomers believe that the deaths of the most massive blue hypergiants may be responsible for some of the long-duration gamma-ray bursts observed in distant galaxies. Not all blue hypergiants end with a visible explosion. Some are so massive that when their cores collapse, they fall directly into black holes with little or no outward display, a process called direct collapse. In such cases, most of the star's mass simply disappears behind an event horizon, forming an object so dense that not even light can escape. The star effectively vanishes from the visible universe, leaving behind only the gravitational footprint of the black hole. Whether a blue hypergiant explodes as a supernova, erupts as a hypernova, or collapses silently into a black hole depends on its initial mass, its rate of mass loss through stellar winds, and its internal structure at the time of death. The aftermath of these deaths is just as significant as the events themselves. A supernova remnant can expand outward for thousands of years, creating beautiful nebula of glowing gas and dust that serve as cosmic laboratories for astronomers. These remnants are also the seeds of new star systems. The heavy elements scattered by the explosion enrich the interstellar medium, ensuring that the next generation of stars and planets has the raw materials needed for rocky planets and eventually life. In fact, the atoms in our bodies, including carbon, oxygen, calcium, and iron, were all forged in the deaths of massive stars, possibly including blue hypergiants. What makes their deaths especially notable is that they are not isolated events. Blue hypergiants often reside in clusters with other massive stars, and their explosions can trigger chain reactions. The shockwaves from a hypergiant's death can compress nearby gas clouds, igniting the birth of new stars. At the same time, the violent radiation from the explosion can strip away material and halt star formation in nearby regions. In this way, the deaths of blue hypergiants reshape entire neighborhoods of galaxies, acting as both destroyers and creators. Astronomers study these spectacular deaths not only for what they reveal about stellar evolution, but also because they are connected to some of the biggest mysteries in astrophysics. Understanding how blue hypergiants collapse into black holes, for instance, provides insights into the population of black holes that permeate galaxies. Similarly, studying their explosions helps refine models of gamma-ray bursts, which are still not fully understood despite their significance as some of the most energetic events ever recorded. In short, blue hypergiants live fast and die violently. Their spectacular deaths are cosmic fireworks displays on a scale beyond imagination. Explosions that light up galaxies, forge the elements of planets and life, and leave behind black holes that warp space and time itself. Their endings may be brief, but their consequences ripple through the universe for billions of years afterward. With their fiery demise now understood, the next step is to explore the legacy they leave behind in more detail. Their role in chemical enrichment, where their violent deaths seed the cosmos with the heavy elements necessary for the evolution of galaxies, planets, and life itself. The role of blue hypergiants in chemical enrichment is one of their most important contributions to the cosmos. While their rarity and spectacular deaths make them fascinating from an observational standpoint, it is what they leave behind that ensures their legacy continues long after they vanish. Through their violent ends, supernovae, hypernovae, or direct collapse into black holes, blue hypergiants seed the universe with heavy elements, enriching the interstellar medium and providing the raw materials needed for the formation of new stars, planets, and even life itself. Without the explosive contributions of massive stars like blue hypergiants, the universe would be a much simpler and emptier place, composed primarily of hydrogen and helium, with very little else. To understand their role, it's necessary to consider the nuclear fusion process that occurs inside stars. In the earlier stages, stars fuse hydrogen into helium. In more massive stars, like blue hypergiants, fusion continues beyond this, creating heavier elements like carbon, nitrogen, and oxygen. As the star evolves and its core temperature rises, it begins fusing even heavier elements such as neon, magnesium, silicon, and eventually iron. However, iron is a dead end in stellar fusion. It does not release energy when fused, which leads to core collapse and ultimately the star's death. It is during this final collapse and explosive death that the real chemical enrichment occurs. In a supernova explosion, the outer layers of the star are blasted into space with immense force. These layers contain all of the elements produced during the star's lifetime: carbon, oxygen, magnesium, silicon, and more. The energy of the explosion also drives nucleosynthesis, a process where elements heavier than iron are created in the intense heat and pressure of the blast. Gold, platinum, uranium, and other rare elements are formed in these fleeting but violent moments. A single hypergiant explosion can create more of these heavy elements than billions of years of quieter stellar fusion combined. The shockwave from the explosion then disperses these elements into the interstellar medium, spreading them across vast regions of space. The importance of this cannot be overstated. The chemical richness of the universe today, the fact that planets like Earth exist, that life as we know it is possible, and that technology built from metals and complex molecules exists, is directly tied to the contributions of massive stars like blue hypergiants. The iron in our blood, the calcium in our bones, the silicon in our planet's crust, and the gold in our jewelry were all forged in the hearts of massive stars and expelled in their deaths. Every element heavier than helium in our bodies and our world is a legacy of ancient stars that lived and died long before the sun was born. Blue hypergiants, because of their size and instability, play an especially large role in this process. Their intense stellar winds eject enriched material even before their final deaths, preceding their environments with elements like nitrogen and carbon. Then, when they finally explode, they contribute massive amounts of newly forged elements to their surroundings. Some of the largest hypergiant eruptions, such as the one Eta Carinae experienced in the 19th century, create massive nebulae filled with enriched gas that can serve as the birthplaces of future stars. This dual contribution, steady enrichment during their lifetimes and explosive enrichment at their deaths, makes them some of the most efficient recyclers of matter in the universe. The scale of enrichment from a single hypergiant is also remarkable. Astronomers estimate that the energy released in one hypernova can disperse several solar masses worth of heavy elements into the surrounding galaxy. These materials mix with interstellar gas clouds, altering their composition and increasing the metallicity of the galaxy. Over billions of years, this gradual process has transformed the universe from its primordial state, dominated by hydrogen and helium, into the chemically diverse cosmos we inhabit today. Every new generation of stars is slightly richer in metals than the one before it, thanks in large part to the contributions of rare giants like blue hypergiants. Another fascinating aspect of their chemical enrichment is its role in galactic evolution. The heavy elements produced and dispersed by blue hypergiants contribute to the cooling of gas clouds, which is necessary for star formation. Metals allow clouds to radiate away heat more efficiently, enabling them to collapse and form new stars. In this way, hypergiants indirectly fuel the birth of future stars and planetary systems. Without the enrichment they provide, the universe might still be filled only with primitive stars and barren gas clouds, with little chance for the complex chemistry needed for planets and life. From a scientific perspective, studying the chemical enrichment of hypergiants provides critical insights into the cosmic origin of elements. Observations of their supernova remnants, such as glowing nebulae filled with enriched gas, allow astronomers to analyze the distribution of elements and refine models of nucleosynthesis. These studies connect the life cycles of stars directly to the composition of galaxies, including our own. They also link stellar deaths to planetary science and even biology, since the elements essential for life originate in events like the deaths of hypergiants. With their contribution to the chemical makeup of the cosmos made clear, we now turn to their broader astronomical importance and why scientists place such value on studying these rare stars despite the immense challenges of observing them. The astronomical importance of blue hypergiants extends far beyond their rarity and spectacle. For astronomers, these stars are more than cosmic curiosities. They are vital case studies for understanding the behavior, evolution, and limits of the most massive stars in existence. Because they occupy the extreme upper end of stellar physics, blue hypergiants act as natural laboratories, pushing the boundaries of what is possible in terms of mass, luminosity, instability, and stellar death. By studying them, scientists gain insights not only into hypergiants themselves, but also into the processes that govern the life cycles of galaxies and the universe as a whole. One of the main reasons astronomers study blue hypergiants is to understand stellar evolution at the upper mass limit. Most of our knowledge of stars comes from observing common types, like red dwarfs, sun-like stars, or red giants, which make up the overwhelming majority of the stellar population. But these stars do not tell the full story. The evolution of massive stars, those tens or even hundreds of times more massive than the Sun, follows a completely different trajectory. Blue hypergiants represent one of the rarest and most extreme evolutionary phases of these massive stars. By analyzing their structure, instability, and mass loss patterns, astronomers can refine models of how the biggest stars live, change, and die. Without hypergiants, our picture of stellar evolution would be incomplete. They are also crucial for studying stellar instability. Hypergiants sit precariously close to the Eddington limit, where the outward push of radiation pressure nearly equals the inward pull of gravity. Few stars exist in this regime, and those that do provide unique opportunities to study how stars behave under such extreme conditions. Their eruptions, variability, and stellar winds offer direct clues about how radiation pressure drives mass loss, how outer layers interact with the core, and how stars can transition rapidly between different phases. Understanding this instability helps explain not just hypergiants, but also other unstable stars, such as luminous blue variables and Wolf-Rayet stars. Another area where hypergiants are invaluable is in understanding supernovae and black hole formation. These stars are destined for violent ends, and their deaths help explain the population of stellar mass black holes scattered across galaxies. By observing blue hypergiants in their final stages, astronomers can connect the dots between a star's initial mass, its evolution, and the type of explosion or collapse it produces. This connection is vital for predicting supernova rates, understanding the distribution of black holes, and explaining some of the most energetic phenomena in the universe, including gamma-ray bursts. Hypergiants, in this sense, are living precursors to cosmic events that astronomers are eager to understand. Their stellar winds and chemical enrichment also make them important to galactic studies. Because blue hypergiants eject so much mass during their short lifetimes, they contribute significantly to the chemical and structural evolution of galaxies. By studying their winds and eruptions, astronomers learn how heavy elements are distributed throughout the interstellar medium, influencing future star and planet formation. In this way, hypergiants serve as key pieces in the puzzle of galactic ecology, showing how matter is recycled from one generation of stars to the next. Observationally, their luminosity makes them useful as cosmic beacons. Because they shine millions of times brighter than the Sun, hypergiants can be detected in galaxies far beyond the Milky Way. This makes them valuable tools for probing distant regions of the universe. Their brightness allows astronomers to study environments and star populations in galaxies that might otherwise be too faint to observe in detail. In some cases, hypergiants can even be used as distance indicators, helping refine measurements of cosmic scales. From a theoretical perspective, hypergiants test the limits of astrophysical models. The physics of such massive stars is extremely complex, involving turbulent convection, intense radiation pressure, rapid mass loss, and dynamic instabilities. Each hypergiant studied provides real-world data that can be compared against computer simulations, allowing astronomers to refine their models. This is particularly important for improving predictions about massive star populations, supernova frequencies, and black hole formation across the universe. In addition, hypergiants offer a window into the early universe. The first stars ever formed, known as population 3 stars, are thought to have been extremely massive, possibly hundreds of times more massive than the Sun. Though none of these first stars survive today, studying blue hypergiants gives astronomers a way to approximate how such stars might have behaved. The insights gained from hypergiants help scientists imagine what conditions were like in the first billion years after the Big Bang, when the universe's first heavy elements were being forged. The importance of studying blue hypergiants lies in their uniqueness. With only about 30 confirmed in the universe, each one represents a rare chance to observe physics in action at the outer limits of possibility. They are not just one more type of star, they are extreme outliers that embody processes most stars will never experience. Ignoring them would be like studying biology, without ever examining the rarest, most unusual organisms that reveal the extremes of what life can do. Hypergiants expand our understanding of the possible, showing us not the average, but the extraordinary. With their scientific value now clear, the next step is to place them in context by comparing blue hypergiants to other types of giant stars, showing how they stand apart even from the universe's other colossal stellar categories. When comparing blue hypergiants to other giant stars, their uniqueness becomes even more striking. While the universe produces many massive stars, few can rival the extremes of blue hypergiants. To highlight this, it is useful to contrast them with two other fascinating categories of stellar objects: red supergiants and neutron stars. Each represents a different path of stellar evolution, and by examining them side by side, we see why blue hypergiants stand out as one of the rarest and most extraordinary stellar classes in existence. Let's begin with red supergiants, such as Betelgeuse in the constellation Orion. Red supergiants are also incredibly large, often even larger in radius than blue hypergiants. In fact, some red supergiants can swell to over 1,000 times the Sun's radius, large enough that if one replaced our Sun, its surface would extend beyond the orbit of Jupiter. Blue hypergiants, by contrast, tend to be smaller in radius, but significantly hotter and more luminous. This makes the two types of stars almost opposites. Red supergiants are vast but relatively cool, with surface temperatures around 3,000 to 4,000 Kelvin, giving them their reddish glow. Blue hypergiants, on the other hand, are smaller in radius but much hotter, with surface temperatures often exceeding 20,000 Kelvin, resulting in their intense blue-white light. Where red supergiants are like colossal, cooler embers, blue hypergiants are like concentrated furnaces burning with searing intensity. Another key difference is in luminosity. While red supergiants are bright, shining tens of thousands to hundreds of thousands of times brighter than the Sun, blue hypergiants can shine millions of times brighter. Their higher temperatures and extreme radiation output make them some of the most luminous objects in the universe, far surpassing red supergiants in terms of sheer energy emission. This is part of what makes blue hypergiants visible even in distant galaxies, while red supergiants, though large, do not project the same overwhelming brilliance across cosmic distances. The lifespans of these two classes also highlight their differences. Red supergiants are typically in the late stages of stellar evolution, having exhausted hydrogen in their cores and expanded enormously as they begin fusing heavier elements. Blue hypergiants, on the other hand, occupy a more unstable and transitional phase, often fluctuating between different stages of massive star evolution. Both types will eventually end their lives in supernovae, but the pathways and timescales differ. Red supergiants may live longer in their swollen state, while blue hypergiants often burn through their evolution far more quickly, sometimes transitioning into luminous blue variables or Wolf-Rayet stars before finally collapsing. On the opposite end of the spectrum, from these swollen, luminous stars, are neutron stars, the ultra-dense remnants left behind after massive stars explode. While blue hypergiants represent the peak of size and brilliance, neutron stars represent the opposite extreme, compactness. A neutron star is typically only about 20 kilometers in diameter, roughly the size of a city, yet it can contain more mass than the Sun. This makes neutron stars unimaginably dense, with a teaspoon of their material weighing billions of tons. Comparing a blue hypergiant to a neutron star illustrates the vast diversity of stellar outcomes. One is huge, unstable, and blindingly bright, while the other is tiny, stable, and incredibly dense. Despite these differences, there is a connection. Blue hypergiants often end their lives as neutron stars or black holes. Their enormous mass means that when they collapse, their cores may compress into neutron stars, or if the collapse is extreme enough, into black holes. In this way, neutron stars are often the final product of stars that once blazed as hypergiants. Observing hypergiants gives astronomers insight into the earlier stages of stars that will later become neutron stars, linking the brightest, most unstable stellar objects to some of the densest and most mysterious remnants in the universe. What sets blue hypergiants apart in this comparison is their combination of extremes. Red supergiants may be larger in physical size, and neutron stars may be more extreme in density, but blue hypergiants combine immense mass, blistering heat, searing luminosity, and profound instability in a way that no other stellar type does. They sit at the very edge of what is possible for a living star, burning with a brilliance that ensures they cannot last long. This uniqueness cements their position as one of the rarest and most fascinating categories of stars ever discovered. With this contrast established, it is worth looking more closely at some of the iconic blue hypergiants that astronomers have identified, stars that serve as representatives of this rare class and provide invaluable data for our understanding of massive stellar evolution. Among the very small population of blue hypergiants that astronomers have identified, a few stand out as iconic examples, stars that have not only captured scientific interest, but also earned a place in astronomical history due to their sheer power, instability, or spectacular eruptions. These stars serve as windows into the rarest category of stellar evolution, helping scientists piece together the puzzle of how such massive, unstable objects form, live, and die. Because there are only about 30 confirmed blue hypergiants in the entire universe, each one is valuable, but some are especially noteworthy for their dramatic behavior and unique characteristics. The most famous of all is undoubtedly Eta Carinae, located about 7,500 light-years away in the Carina constellation. Eta Carinae is one of the most massive and luminous stars ever discovered, with a mass estimated to be between 100 and 150 times that of the Sun, and a luminosity several million times greater. What makes it iconic is not just its size and brightness, but also its instability. In the 1840s, Eta Carinae underwent the infamous Great Eruption, during which it expelled an enormous amount of material, equivalent to several suns' worth of mass, into space. This eruption temporarily made it the second brightest star in the night sky, despite its immense distance. The ejected material formed the spectacular Homunculus Nebula, a pair of glowing lobes of gas and dust that still surround the star today. Eta Carinae has remained highly unstable ever since, with astronomers monitoring it closely for signs of another eruption, or even an impending supernova. It is often considered a prime candidate for one of the most dramatic stellar deaths humanity may ever witness. Another well-known example is HD 33579, located in the Large Magellanic Cloud, a satellite galaxy of the Milky Way, about 160,000 light-years away. This star is remarkable for being one of the most luminous stars known, with an estimated luminosity of nearly 1 million times that of the Sun. Unlike Eta Carinae, HD 33579 is relatively stable for a hypergiant, which has made it particularly valuable to astronomers. Its unusual steadiness has sparked debates about its precise classification, but most agree that it belongs in the rare category of blue hypergiants. Because of its relative stability, it provides scientists with an opportunity to study a hypergiant in a quieter phase, helping them understand how these stars transition between different stages of massive star evolution. In our own Milky Way, another notable hypergiant is HD 80077, located in the constellation Carina, not far from Eta Carinae itself. With a luminosity hundreds of thousands of times that of the Sun and a mass loss rate that reveals strong stellar winds, HD 80077 demonstrates the instability that defines hypergiants. Though not as famous as Eta Carinae, it plays an important role in expanding the small catalogue of hypergiants available for study within our galaxy. BP Crucis, also known as GX301-2, is another fascinating hypergiant in the Milky Way, located about 12,000 light-years away in the constellation Crux. What makes BP Crucis especially interesting is that it is part of a binary system, paired with a neutron star. The hypergiant's powerful winds feed material onto the neutron star, producing intense X-ray emissions. This unusual interaction allows astronomers to study how hypergiants behave in binary systems and how their instability can drive high-energy processes far beyond visible light. There are also hypergiants outside the Milky Way that deserve mention. Cygnus. OB2 number 12, for example, is one of the most luminous known stars in our galaxy, situated about 5,000 light-years away in the constellation Cygnus. Though not as well known as Eta Carinae, it is considered one of the brightest stars in the Milky Way, shining with millions of times the Sun's luminosity. Its classification as a blue hypergiant makes it a crucial object for studying the upper boundaries of stellar brightness and instability. What makes these iconic hypergiants especially valuable is their diversity. Eta Carinae represents extreme instability and eruptive behavior. HD 33579 offers a rare case of relative steadiness. BP Crucis highlights the dynamics of a hypergiant in a binary system. And Cygnus, OB2 number 12, pushes the limits of luminosity. Together, they provide astronomers with case studies across the spectrum of hypergiant behavior, helping to build a more complete picture of what defines these stars. Even though only a handful of blue hypergiants are known, the iconic ones stand out not just as rare cosmic objects, but as benchmarks in the study of stellar physics. They embody the different faces of hypergiant instability, from steady brilliance to explosive eruptions, and from solitary giants to interactive binaries. Each one represents an irreplaceable piece of data in the effort to understand how the universe's most massive stars live and die. With the iconic examples covered, it is important to note that despite all we have learned, blue hypergiants remain deeply puzzling. Their rarity and instability leave many unanswered questions, which brings us to the mysteries that still surround them. Questions that continue to drive astronomers to study these rare giants more closely. Despite decades of study, blue hypergiants remain wrapped in mystery. Astronomers have learned a great deal about their size, brightness, instability, and role in enriching the cosmos. But some of the most fundamental questions about them remain unanswered. These questions revolve around why they form so rarely, what drives their extreme instability, how they evolve compared to other massive stars, and what precisely determines whether they end as supernova, hypernova, or direct black hole collapses. Each of these puzzles underscores how little we still know about the universe's rarest giants and why they continue to fascinate scientists. The first great mystery is why they form so rarely. Out of an estimated 200 billion trillion stars in the observable universe, only about 30 blue hypergiants are currently confirmed. While it is understood that forming such stars requires immense molecular clouds with enough mass to produce a stellar giant in one collapse, the exact conditions that allow this process to happen are still poorly constrained. Why do some massive stars evolve into hypergiants while others, born in the same region with comparable mass, end up as supergiants, luminous blue variables, or Wolf-Rayet stars? The rarity suggests that the pathway to hypergiant formation is extremely narrow, but astronomers have yet to pinpoint the precise triggers. It may be related to the amount of angular momentum during formation, the metallicity of the gas cloud, or even interactions with companion stars. But so far, there is no single model that cleanly explains why only a handful of massive stars evolve into hypergiants, while others do not. Another unresolved puzzle involves their instability. Blue hypergiants are defined by their chaotic behavior, but the mechanisms driving their extreme mass loss and periodic eruptions are not fully understood. Stars like Eta Carinae undergo massive outbursts that expel several solar masses of material in just a few decades. Yet astronomers cannot fully explain why such events occur. Some models suggest that instabilities deep within the star's fusion zones cause sudden surges of energy that disrupt the outer layers. Others propose that rotation and magnetic fields may play a role, creating asymmetries that destabilize the star's atmosphere. Binary interactions are another candidate. Many hypergiants appear to exist in systems with companion stars, and the gravitational pull from a companion could stir up instability or channel material away. Untangling which of these factors dominate remains one of the major challenges of hypergiant research. Linked to this is the mystery of how hypergiants transition between phases. Many astronomers believe that blue hypergiants are not a permanent classification, but rather a temporary stage in the evolution of the most massive stars. For instance, some may begin as blue hypergiants before shedding enough mass to become Wolf-Rayet stars, while others may pass through a luminous blue variable phase on their way to supernova. But the exact evolutionary tracks remain uncertain. How long does the hypergiant phase last? Do all hypergiants eventually become luminous blue variables, or can some bypass that stage? Observational evidence is limited because of their short lifespans and rarity, leaving scientists with only fragments of their evolutionary story. A related mystery involves their endings. While we know that hypergiants ultimately collapse into supernovae, hypernovae, or black holes, the deciding factors are not yet clear. Does the amount of mass lost through stellar winds determine whether a star explodes or collapses silently? Or does the initial mass of the core play a larger role? The case of Eta Carinae is particularly intriguing. Some astronomers predict it will go supernova in the near astronomical future, while others argue that it might collapse directly into a black hole. Understanding what controls these outcomes is critical, not just for stellar astrophysics, but also for explaining populations of black holes and the origins of gamma-ray bursts. There are also unresolved questions about metallicity and environment. Metallicity refers to the abundance of elements heavier than hydrogen and helium in a star's composition. Stars in galaxies with lower metallicity, such as the Large Magellanic Cloud, may evolve differently than those in the Milky Way, where metallicity is higher. Does metallicity make it more or less likely for a massive star to pass through a hypergiant phase? Do galaxies rich in heavy elements suppress hypergiant formation by increasing mass loss, or do they enhance it by creating conditions that favor instability? These are open questions that astronomers are still working to answer, and hypergiants in the Magellanic Clouds are critical case studies for testing such theories. Another puzzle lies in binary interactions. A significant fraction of massive stars exist in binary or multiple systems, and some hypergiants, such as BP Crucis, clearly have companions. These interactions may be crucial in explaining hypergiant behavior. For example, mass transfer between stars could destabilize the hypergiant, triggering eruptions or altering its evolution. In extreme cases, mergers between massive stars may even create hypergiants, suggesting that some could be the products of stellar collisions rather than standard formation. However, because hypergiants are so rare, astronomers have limited opportunities to study these systems in detail, leaving many aspects speculative. Even the duration of the hypergiant phase remains uncertain. Do blue hypergiants live for hundreds of thousands of years as hypergiants, or only tens of thousands? Their overall lifespans are measured in millions of years, but the hypergiant phase itself may be very short, making it even less likely for us to observe them. This helps explain their scarcity, but it also complicates attempts to model their evolution. Without knowing how long they remain in this stage, astronomers struggle to determine how many massive stars might pass through it during their lives. There are mysteries about observational biases. Because hypergiants are so luminous, they can be seen across large distances. But distinguishing them from other massive stars requires precise spectroscopic analysis. It is possible that some stars we currently classify differently might in fact be hypergiants, or that others remain hidden behind dust clouds. Our current catalogue of about 30 may not represent the full population, but given how extreme these stars are, scientists agree that their numbers will never be large. The question is whether dozens more remain undiscovered, or whether the 30 we know truly represent most of the hypergiants that exist within our observational reach. In essence, the mysteries surrounding blue hypergiants revolve around fundamental questions of stellar physics. Why do they form so rarely? What processes drive their instability? How do they evolve? And what controls their ultimate fate? Each of these questions touches on larger themes in astronomy, from the life cycles of galaxies to the creation of black holes and heavy elements. The fact that so many uncertainties remain, despite decades of study, underscores just how unusual and enigmatic these stars are. They are not just rare in number, they are rare in understanding too. With so many unanswered questions, it is clear that blue hypergiants are among the most puzzling stellar objects known to science. And this is precisely why they hold such a unique place in astronomy. They are the rarest of the rare, existing only briefly, under extraordinary conditions, and challenging our understanding of what stars can be. Blue hypergiants are, without question, the rarest of the rare when it comes to stellar phenomena. In a universe teeming with stars, an estimated 200 billion trillion spread across billions of galaxies, the fact that only about 30 blue hypergiants are confirmed to exist underscores just how exceptional they are. While other unusual stellar objects, like neutron stars, magnetars, or even black holes, are considered exotic, they are still far more common than blue hypergiants. This places hypergiants in a category all their own. Stars so rare and fleeting that they represent an extreme outlier in the cosmic population. The rarity of blue hypergiants is the product of multiple overlapping factors. They require extraordinary birth conditions, forming only in the most massive molecular clouds with just the right balance of mass, density, and dynamics. Most clouds fragment into smaller stars, but for a hypergiant to form, an unusually large portion of the cloud must collapse into one single star. Even when that improbable event occurs, the star's immense mass makes it unstable from the very beginning. Stellar winds and eruptions often strip away enough mass to prevent the star from maintaining hypergiant status for long. This combination of difficult formation and fragile existence ensures that only a handful can ever exist at one time. Their rarity is further amplified by their short lifespans. While common stars like red dwarfs live for trillions of years and sun-like stars endure for billions, blue hypergiants burn themselves out in just a few million years. This fleeting timescale makes it statistically unlikely for observers, like us, to catch them during their brief existence. Many more hypergiants have almost certainly formed and died over the 13.8 billion year history of the universe, but we see only the tiny fraction that happens to exist right now in this cosmic moment. In a sense, their rarity is not just about how few exist. It is also about how rarely they overlap with the time frame of human observation. Another layer of rarity comes from classification itself. Blue hypergiants occupy an extremely narrow window in the spectrum of stellar evolution. Many massive stars evolve into red supergiants or Wolf-Rayet stars without ever passing through a hypergiant phase. Others may only briefly become hypergiants before rapidly shedding mass and transitioning into another classification. This makes the hypergiant stage not only rare in numbers, but rare in duration, a fleeting identity in the life of only the most massive stars. Compared to other unusual stellar phenomena, hypergiants stand apart. Neutron stars and black holes are spectacularly exotic, yet they are the end states of many massive stars, making them relatively common in galactic populations. Magnetars, while rare, number in the thousands within the Milky Way alone. Supernovae occur regularly across the universe, with astronomers observing them in distant galaxies on a routine basis. But blue hypergiants are different. They are not the end state of many stars, but a rare and unstable phase that only the universe's largest, most luminous stars can briefly occupy. Their rarity is therefore twofold. There are few of them to begin with, and each one only exists in this form for a tiny fraction of its life. Their scarcity also makes them astronomically precious. Every confirmed blue hypergiant becomes an essential object of study because each one offers unique data about the upper extremes of stellar mass, luminosity, and instability. With only a few known, the scientific community pays close attention to all of them. Eta Carinae, for example, has been observed intensively for over a century, with astronomers monitoring its brightness variations, eruptions, and stellar winds for clues to hypergiant behavior. In many ways, each hypergiant is treated like a rare jewel, unique, irreplaceable, and invaluable for our understanding of the cosmos. The phrase "rarest of the rare" also captures the way hypergiants stand out in human imagination. While stars like the Sun are relatable and stable, hypergiants are distant, powerful, and nearly incomprehensible in scale. Their scarcity heightens their mystique. We are not just looking at another bright star, but at one of the rarest objects in the known universe. If you consider how vast the cosmos is, with its seemingly infinite abundance of stars, the ability to count the number of confirmed hypergiants on just a few dozen fingers is extraordinary. It is a reminder that the universe, for all its immensity, still produces phenomena that are astonishingly selective and precious. From a cosmic perspective, their rarity also has profound implications. Blue hypergiants are rare not only in number, but also in their impact. Despite being so few, they influence their surroundings disproportionately. Their stellar winds, radiation, and explosive deaths enrich and shape galaxies, meaning their rarity does not diminish their importance. In fact, it emphasizes how powerful they are. Even though there are only a few, their contributions to galactic chemistry, black hole formation, and stellar dynamics are immense. In summary, blue hypergiants are the rarest of the rare because their existence depends on nearly impossible conditions. They live for only a fleeting moment, and they occupy an evolutionary phase so unstable that few stars can sustain it. Their scarcity makes them both scientifically priceless and cosmically profound. Among trillions upon trillions of stars, they stand as exceptions, brilliant, unstable, and vanishingly few. With their rarity firmly reinforced, we now move to the closing reflection. A final look at what blue hypergiants mean in the grand tapestry of the universe, and why, in a cosmos filled with abundance, such extremes remind us of the rarest and most fleeting wonders of all. In the vastness of the universe, stars are everywhere, from the smallest red dwarfs that quietly burn for trillions of years to the bright, steady suns that anchor solar systems like our own. Stars form the backbone of the cosmos. They are so numerous that even if you were to count them every second for the rest of your life, you would not come close to tallying the 200 billion trillion stars believed to exist in the observable universe. And yet, among this ocean of light, there exists a category so rare, so fleeting, and so extreme that it almost feels like an astronomical miracle: the blue hypergiant. Out of all those countless stars, astronomers have confirmed only about 30. That number is almost absurd in its smallness. 30 stars among hundreds of billions of galaxies, each galaxy filled with billions of stars of its own. 30 outliers in a universe of staggering abundance. Their rarity is not an accident, but the product of impossibility stacked on impossibility. The conditions needed to form them are extraordinary, requiring massive clouds of gas and dust and the perfect balance of gravitational collapse. Their lives are precarious, defined by instability and violence, burning so brightly and so furiously that they can exist for only a few million years before collapsing in spectacular destruction. They are stars that should not exist for long, and yet, somehow, a handful of them do, and we are fortunate enough to observe them. Blue hypergiants embody cosmic extremes. They are not simply large, they are colossal. They are not just luminous, they shine with the brilliance of millions of suns. They are not stable, they are constantly tearing themselves apart with stellar winds, eruptions, and mass loss. And they are not long-lived, they flicker out in cosmic moments, leaving behind black holes or remnants of supernovae that reshape their galactic neighborhoods. To encounter one, even through the lens of a telescope, is to witness the absolute edge of what nature can create before collapsing under its own power. The fact that only around 30 are known makes them as scientifically precious as they are rare. Each one studied adds to our understanding of stellar physics, supernovae, chemical enrichment, and the birth of black holes. They are extreme test cases for theories, proving grounds for astrophysical models and signposts of the most intense processes in the universe. Without them, our picture of how stars evolve and die would be incomplete. With them, we glimpse the full spectrum of stellar possibility, from the smallest embers to the brightest and most unstable titans. But beyond their scientific value, their rarity has another effect. It forces us to recognize how precious cosmic extremes really are. In a universe where abundance is the rule, where stars and galaxies number in unimaginable quantities, blue hypergiants are the exception. They remind us that even in the immensity of space, not everything is plentiful. Some phenomena are rare by nature, appearing only briefly under extraordinary conditions and disappearing forever. So, when we look out into the night sky and imagine the countless stars that fill it, it is worth remembering that only about 30 of those stars are blue hypergiants. They are the rarest of the rare, fleeting titans that blaze with unmatched brilliance before collapsing into darkness. They are reminders that the universe does not just produce stars, it produces extremes. And those extremes are precious precisely because they are so few. In the end, blue hypergiants are not just stars. They are cosmic rarities, proof that even in a universe of near infinite abundance, rarity still exists, and it shines brighter than almost anything else. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.